So hello everybody. So now something not quite completely different. We want to bring you in the very weird world of programmable logic controllers. And you ask yourself, what does this have to do with Erlang or Elixir? Well, it does, because we wrote a compiler for one of their languages. And that's what we want to show you about, including an IDE. So what is a PLC or programmable logic controllers? It's the computers that make everything run. Like from your garage door opener. Yeah, maybe that's like a ready-made box, but like custom-made garage door opener is usually driven with a PLC. So that's a few form factors of like all the PLCs. You have on one side a little box with a PC in, or with some kind of embedded controller in. And then the field on the side is basically wiring for I/O, usually 24 volts. So this is like for industry. It's the computers that make industry run also, like factories run on PLCs, basically. And there's a whole probably disjoint group of us here in the room of PLC programmers who know their PLC languages and which we don't know. Who knows a PLC language? Who wrote ever any code in a PLC language or have seen it? You? No, PLCs. It's a... No? Yeah, okay, so it's totally disjoint from this room. Very cool. But it's a pretty large group of programmers, and they're very asked for. So if you're kind of like out of a job, learn a PLC language and learn how machines work, because that's kind of like the application-specific knowledge they have. They know how to get machinery to work. And then they use their languages. So there's a few standards for these PLC languages. One is called IEC 61131. That's the classical PLC standard. And it includes like a whole set of languages, graphical and non-graphical ones. And then there's a new standard, which means it's only 20 years old. It's brand new. It's not fully adopted yet, and that tells you something else about the PLC programmers. They are very conservative. They stick with what they know for a very long time, because they write applications with other time spans. If you have a PLC application, it usually runs for 20 years until it's like dismantled. And then some big companies, one big European company starting with an S, has their, I can say it, it's Siemens. They have their own standard, which is very similar to 61131, but different. But they have so much market penetration in Europe that they can actually afford this. So how are these things programmed? How do these programming languages and graphical representations look? So that's another picture of PLCs. I don't know why I put this there. So that's how it started. It started actually at Ford in the US. So before PLCs, when the machinery, like on a conveyor belt, a machine that needed to do a sequence of steps was programmed, you used relays. Like you had coils, and the coils like operated switches, and there were a few specialized relays, which has a delay. Like when you put it on, there's a capacitor charging, and then the switch goes on after a while. And you can like have a little dial on the front to set the delay. So there's all these relays. And to not get confused, they have the electricians had a way of drawing these circuit diagrams for specialized relay circuit diagrams, which are called ladder diagrams. And that's what you see on the left. That's a ladder diagram, a very small one. In ladder diagrams, you have like some special symbols for coils. That's the round braces. That's a coil, which is basically kind of like an output, an actuator, because it's the coil of the relay. And these coils then are connected to switches and switch on or off. And then when there's a slash inside, that's meaning a not. So it's like switched off when the coil goes on. And the coils have names, and the names kind of like interconnect these things across layers. So you have multiple layers of these things. That's why it's called ladder diagrams, because it looks like a ladder. And that's what the electricians drew up when they wired the machine. Electricity. Ford found this like kind of like tedious that the electrician has to come in and like rewire the whole electricity stuff whenever they wanted to change a little thing in their process. So they thought, wouldn't it be cool if we could actually make this wiring programmable? And that kind of like was the birth of the first PLC. So, and that's also the first language. The first language for PLCs was ladder diagrams, because that was the thing that was used. And they were not actually real computers. They were like memory with special logic on it. And the ladder diagram was translated into memory values and then just sequenced through. Like that's where kind of the sequential thing comes from. Because one thing that the old PLCs all have in common, they run in a loop. Whatever you program, in whatever language you program it, it's translated into one big loop, which constantly runs in a loop. And that's your real-timeness. So twice the loop time is your real-time reaction time, your worst case. So you basically wrote your program, you measure your loop time, or it actually gets displayed. And when it's too slow for your process, you buy a larger PLC, because then your PLC is too slow. It's a very wasteful way to do things. But that's basically how most of the PLCs still run. The other syntax that you see on the side that looks like assembler, and it's very similar like assembler. You have load and store and registers. That was the second language that was added. So you could more like program logic in this, but it was still very simple. And then later on, so this was all a sequence of standards. Basically, there were more and more languages added with time. Later on, they made a thing called structured text, which is a Pascal-like language, because that was a language that was widely used when it was actually designed. So you have this like colon equals thing for assignment, and it's case insensitive. That's all kinds of like, it all smells like Pascal, the whole syntax. But it has specialized types for PLCs, like data types for time deltas, or data types for wall clock time, and specialized fixed point data, and all kinds of things. And there's also a representation of the thing, and it's actually, I think, I put the same program that's in structured text down there as function blocks. So those little boxes are kind of like functions. So it's a functional, it's actually, you could say it's almost functional reactive programming. It always has a data flow approach, even if you write it in structured text. Which is kind of like, by this constant looping thing is then synchronous data flow, basically. So because in every loop, you progress your data flow once further. And then there were higher level representations. That's sequence function charts. That's actually the most used one in PLC programmers for complicated processes. This is modeled after Petri nets. Who knows Petri nets? A few? So Petri nets is kind of like, well, very handy if it's a state machine which can be in multiple states at the same time, like a concurrent state machine, basically. And you have like special operators like this bars where you can actually have a join. Like when both incoming states are on, then the outgoing states gets on, and there's a whole logic behind it and a whole theory behind it. And sequential function charts were used for this, and that was useful because you can have concurrency then. But now to the future, which means 20 years ago. There was the idea that it would be cool that you would do distributed programming with PLCs, which you could do ad hoc with like hooking it up to a field bus, and it runs in cycles, and then you cyclically send data over the field bus, which then results in interesting effects when the cycle times kind of change. So it's a tar pit of race conditions, the whole thing. So you add a little code, an unrelated line of code to one of the PLCs, cycle time changes, suddenly your process doesn't work anymore. So that's not good. Of course, you can make your own handshakes with the synchronous thing, and you need to, but that's tedious. So the standardization committee kind of like thought it would be cool that we don't run in cycles all the time, and we don't do synchronous data flow, but do asynchronous data flow. So everything is now modeled around events. So that's the thing, the extra data they added. So it's still a function block. So it's still, this box is a function block, implementing a function with state. And we see more of those in ours later on. But this has like a kind of like head and a body. And the head is events. On the left is inputs, on the right is outputs. And the body is data. And the data is only valid when a connected event triggers. So it's only sent and valid. So it's not sent all the time, but it only needs to be sent when the event triggers, basically. Which we then, I'm getting ahead of myself, which kind of like maps very nicely to messages, by the way, like event plus data message. Think message, then you're in Erlang land. And that's how we got there. And these vertical lines is basically the showing which event kind of like is joined with which data. Like A, B, and C is only valid when the vote event triggers. And then it does its machinery, and then voted comes out, and then a state is triggered. And usually these event flows with data, so you have basically, you need an event wire from input to output. Sometimes you can then diverge, or sometimes you're only interested in the event because you're only interested when something happened, not like what the data, according data is. So it can diverge, but often it runs together. So what we did here is we wrote a compiler for this language a while ago, and the compiler compiles to Beam files. That's the summary. And the details for the compiler and the runtime, I hand over to Barbara.
So now that Pierre explained how the PLC worked, I can explain how we compiled and run. So we use regular expression based on lexical analyzer generation for Erlang. That's very similar to Lex. And then we have YAC, which is a parser generator, and we create core Erlang. And core Erlang is a subset of Erlang, which doesn't have or takes out the synthetic sugar that the compiler doesn't need, and then Cyril help us generate these core files because it's a module that defines the abstract data type for representing core Erlang.
By the way, it's not documented.
Yes.
It's an LDoc. If you want to find it, it's an LDoc.
And in the compiler first, when we compile an SD file, we scan these files to generate tokens. The parser uses the tokens and grammar to create an AST, Then the AST is transformed into another AST, but it's still an AST just with different stuff in it. And the AST card creates an Erlang, a core Erlang, then we compile to create the bin file. And
so the normal Erlang compiler is used for that?
Yes.
You can just stuff
Yes, all of this is for free because we have it on the OTP. Did I miss one?
Yeah, the runtime.
Oh, I'm sorry.
No? Yeah. Like.
Okay. No, but okay.
On the right.
Yes, yes. And so once we have these bin files, then these give us the behavior implementation, and I can explain the runtime more detailed. So it is a normal supervisor tree that interacts with the app, and then we can have multiple behavior implementation and each of one of them are a process, and it behaves like a gen server, right? Do you want to expand more on that?
Yeah, so maybe I'll take the mic so it's recorded. So the details is the PLC F block things, that's corresponding to the gen server module. It's the behavior implementation, so it contains a process. Every function block is a process, and our compiler only generates callback modules, which makes them much more easy to test and to reason about. So this is This is not only advantages if you write the code yourself, it's also actually advantages if you generate this code, because it's much easier to kind of like understand if a callback module is correct. You can very easily statically test it. And basically the behavior implementation has all the logic for the processor in like Gen server, but not quite like Gen server, because we need to do different things. And there's one thing missing. On the left, you see there's like a green and red thing in the supervisor. You can also write the callback module in Erlang, which you need to do if you want to write the basic library for this PLC language that interacts with the Erlang world. And that was the whole point, that the PLC programmer can build something that can interact with one of our Erlang embedded systems, basically. So we open this up to PLC programmers. And then you can write your own callback module, but you still need a ST file to define the interfaces. So you can have both, and they work together.
Thank you. And then, of course, Machine uses GRiSP protocol and CRDTs to start up, for the startup phase, I'm sorry. And, but actually, we, okay, let me start all over again, yes. Yeah. So we initialize them each,
so we're doing distribution now.
Yes. So I'm sorry, about the distribution. When we have the callbacks in the runtime, first we initialize them, and then the monitor, when everything is already initialized, the monitor starts send the start messages and sync up with Machino, and then Machino uses GRiSP and CRDTs to start the startup phase coordination. That's so correct, right?
Yeah, the background is that basically everything needs to be ready, because the PLC language doesn't like it when you lose an event. It depends on all events are reliably sent. So we kind of like need to make sure that everything is synced up at the same time. So all the nodes that have parts of the application are ready, and all the processes are ready to receive messages, because that's what we map it to, the events and data. And basically Machino is like a distributed component that uses GRiSP protocols, because this also runs in a mesh network, so it does not need a fully connected Erlang distribution. So it's made for mesh networks, because we have these in manufacturing a lot. Like you go along a conveyor belt, for example, and basically when all function blocks of one supervisor are started, then this monitor gets started, and monitor talks to Machino, like the blue one. Talks to Machino is the one on the bottom that kind of like coordinates the whole thing, and basically tells it, yeah, we are ready to go. And then when everybody's ready to go in the whole network, then Machino gives a signal back, basically everybody's ready to go, and then the monitor sends start messages to all its own function blocks and tells it, yeah, go ahead. And then actually message sending starts, before everybody just gets booted.
This is not a domain that I'm enormously familiar with, but is the basic idea that you're deploying embedded devices which are running Erlang, and they're being used to deploy the code onto the PLC devices? Is this like for that kind of distribution? Or?
We have embedded devices that run Erlang, like based on GRiSP, basically. Okay. And these embedded devices have other logic, and the PLC stuff is usually that the PLC programmer can add its own logic. Okay. That like own logic for the machine-specific logic. And there you want to have the domain-specific language of the people who actually know this stuff.
And are these devices something that you burn once, or they could be updated?
Could be anything. Could be small, can be updatable. Okay. This can also run in the cloud, or on 5G nodes if you want to be like modern, like you have like cloud 5G nodes, edge computing. We can do all this, because wherever we bring the Erlang VM, this works. Just need to make sure the distribution works everywhere. That's actually what we're working on, like make distribution work across the whole edge. I think we're ready for the demo now. So while Barbara sets up the laptop, I show you the hardware. So we brought hardware demo. So that's two GRiSP boards on these two tables. Can anybody see You can see the GRiSP boards? Yeah, good. So you see the LEDs are doing things. And that's supposed to be a traffic light. Okay. Traffic light, for traffic light you actually need 3 LEDs, but we only have 2. So we needed to fake it a bit. But then on the other hand, there's never more than 2 on at the same time. So basically, the red light is alone in itself. So that's red. And after red, it gets, it's really slow. It's a real traffic light. Red and yellow, and then it goes green. And that kind of faked this with two LEDs in the PLC application, actually. And that's how this application looks. And that's also how the IDE looks. So that's the second part of the talk, basically. Not only did we build a compiler, but in the last year we built an IDE for the compiler. Because what the PLC programmers really love is graphical stuff. They want to actually, they're electricians. They want to draw wires. And that's, is this visible very well, the wires? Yeah, okay. When you can you highlight a few? So when you hover over, then it highlights the connections. So you can actually orient yourself. And yeah, that's maybe good. So you can actually look into this. And you see that if you look into this, that the values light up. And they change. Because that's what you see is the live view of the distributed application in these 2 GRiSP boards. So the laptop is hooked up into the same Erlang distribution network over this little Wi-Fi hotspot there. And over this distribution network, the traffic lights coordinate each other. So you should not be able to catch them both green. That would be bad. That's kind of like the maximum failure mode for a traffic light, be stuck in green. And we could even have like a fallback mode, like when the network is not working, you can actually start another application and it's yellow flashing, but we didn't bring that. So you start a local application, basically. That's the non-networked thing. So I think is this working with the mic, or you can maybe use this mic for the demo?
Do you hear me?
To show the elements, what can be done.
Yes. So what Pierre was saying, that when one GRiSP is red, the other one is green, and you can see the values over here. So we have red 1, it means that this is green, or now this is red, but this one is now green. And those are ample applications. And
ample is the German word for traffic light.
Yes.
It's much shorter.
And I can speak about what do we have inside a function block. So on your left side, you can see the actual code for the ample function block. And we can see that we have events in and events out. Events in are on your left. Yes. And on your left. And what the first one says that, okay, we have a go input, and then we have a set yield input with yield, and the with word means that this event, it's only valid, or the data is only valid when the event is triggered, the yield data. So that's the connection. The same for event output. In this case, we have 3 events, and two of them has data, or the data is valid when the event is triggered. And then we also have the state machine, which is this one. And this graph over here is to represent the state machine. First, we have the states, and when we enter in a state, the state can have can trigger an algorithm. Can run an algorithm and then trigger an event. The first one is in it, doesn't have any algorithm or triggers any event. Then we have the RRST event, and this, yes, the second one. And this has an error algorithm, and after running the error algorithm, triggers the set event. And that's why we have over here, let me see, I can do it. But This is the state, this is the algorithm, and then the event that is triggering after the algorithm.
So algorithm is a piece of sequential code that you can run. Like
Yes.
you can have ifs in case, and you can even have loops. And they're down there. That's the algorithms. And they're kind of like always associated with like states when they're entered. And when the algorithms are run, output events are triggered.
Exactly.
And that's the graphical representation you have, because you can't point that good. That's the state. The red thing is the algorithm, and the white thing you see here, that's the output event after the algorithm. That's the standard representation of
Yes,
this.
and we could also have a condition on this transition. So, for example, in this case, can yield to YST. It only triggers if yield is 1. Correct. And also, one thing that we could also have is that we can trigger several events without having several algorithms. So for example, on, I believe it's this one, we can trigger the algorithm, then, run the algorithm and then trigger set, and just after that, trigger other event. Is there something else that you want to explain on this?
Yeah, that's basically, this is, these transitions are triggered by events, and that's actually triggered by not an event. Like there's no event whenever it gets into this state, and this condition is true, it actually does the next transition immediately. But you can have both, like you have if it's in brackets, it's basically a condition, but you can have like an event and a condition. You can say, if this event triggers and this condition is true, then do this transition. So it's a pretty complete state machine implementation.
Mm-hmm.
It's a little bit weird because you do 2 transitions per thing, because the whole semantic is like first you trigger an event, and then you do a transition with it. And then after everything is run, you do another transition, or you see if you can do another transition which is not dependent on the event. So you do a double transition basically on every step. It's kind of like the extra semantics. And what's missing now is, I mean, since the things are still running, what we did not get to before the conferences, of course we also want to show the state machine in which state it is. So it actually should jump around here. It's still missing.
Yes.
Come up here.
One thing that you could do right now is that you could also, should we edit something or after? No, okay.
Oh, yeah.
Oh, okay.
By all means.
Okay, well, we could use this and edit the application that we have right now. So
Oh,
if I,
you can edit the function block.
yes, so if I stop the application like I did.
You need to stop now. Sorry.
And then edit this, I could remove the data that we have and set yield, and we can actually see that after compile. So there is no longer the connection between the event and the data on your left. And we could also change the state machine on it. So we could remove transitions, and this will compile and return, and the returning is our new state machine for this function block.
So basically auto-compiles like after you stopped typing for a while.
Yes.
That's why there's a pause.
Yes.
It's not the compilers that slow.
No, it's not that. Okay. How are we on time?
That's okay. Demo is good.
Okay.
Maybe remove a few connections.
Yes.
So while you do this, so the layout you see here, the whole like connections, that's auto layouted. Nobody drew this. We only have the source code, and the layout is generated. And we will talk a little bit about the algorithm because we wrote this in Erlang. So this is relevant for the conference.
Yes. And on this view, you have your code on your left, and this is the code for the whole application, the layout that you're seeing right now. And first, we have the function blocks, and then we define the event connections. And
Yeah, just delete a few things.
Yes.
And see that it auto layouts.
we delete we wait for the compile, and then we can start again the application. Let me delete more. Event, where is it? Did I remove all
delete all the events. That's good.
Yes, yes. Okay.
So it wouldn't work anymore, but yeah. We only want to show the layout process.
Exactly.
So
once
layout it
we
again.
compile-
Much simpler now.
Yes.
But it still keeps working because we actually didn't add the code that we loaded into the
Into a distribution.
We didn't get to that.
Yes.
That's next. We can do it locally if we run this on one node, but we kind of like need to have the code that we kind of like RPC into all the nodes and kind of like stop the application and restart the application and load the code. It's not much, but yeah.
Yeah.
Conference is a fixed deadline. Okay, I think.
Okay. And then we
Go
can
back to
go
the
back
slides.
to the slides. Yes. It's in the other.
Yeah. Maybe can you hold? Actually, I should have got this one demo. Next slide.
Yes.
Play. And that's still you.
Yes. So now I can explain a bit more about how we create the user interface.
Oh, no, it's not. I double tapped. Now it's correct.
Okay.
Now it works.
Yes. So of course we spoke already about Erlang, but then in the front end we are using JavaScript. Usually an IDE consists of what you already saw, which is list source code, build, auto-compilation tools, and a debugger. So we wanted to build, of course, an Erlang application, but we also wanted a dynamic language in the front end, and that's why we chose JavaScript. Okay. The communication between them is very simple. We create a WebSocket connection with Cowboy, and this allows us to pass and receive messages which are kind of like JSON-like strings to feed our client. We decided to build our entire front end with 3 additional libraries besides JavaScript, which is Vue.js, CodeMirror, and V3 for the graphs. Vue.js is a progressive library for building interfaces. It is focused on how we handle the view or a view layer. So this allows us to create templates that we can just pass the data that we receive from Erlang, the actual messages, to these templates and feed the whole view. Then we use CodeMirror, which is a versatile text editor implemented on JavaScript for the browser. And it's specialized for editing code and has the option to write your own mode, which consists of a set of lexical directives for language that you want to support on your website. And so we added the syntax highlight and the auto-completion for structured text. And also, CodeMirror allows us to define some key buildings and implement search and replace terms.
So it's very complete. You can work with it.
Yes. We also use D3, which allow us to bind arbitrary data into the document object model, which is the DOM, and then apply that data-driven and transforms to this document. We don't use it to create the actual layout because that's being done on Erlang, and Pierre will expand more on that. But we do use it to do some zoom in and out animations and update some events that are given from us from the backend. D3 is a really big library, which we don't use everything on it. We only pick a few modules for the direct cycling layout, which are the state machines graphs. And then we use the zoom module that allow us to pan and zoom the graph in our IDE.
Sound like my area, automatic layout. So the state machine graph we don't do in Erlang, because for that you can actually get nice libraries that run in the front end and they do this. But for the complete layout of like a kind of circuit diagram, because that's what it is, what? Where do these numbers come from? The numbers shouldn't be there. Ignore the numbers. Animation failure. So for the circuit diagram layout, we need a more complex procedure. That's not that easy, and I'm trying to explain you in a very quick and hand-wavy way how this algorithm actually works and how we implement it in Erlang. So one thing is digraph is your friend. For this, very useful. Lots of graph algorithms in there. And what we do is we simplify the whole thing at first. So that's kind of like a different approach that you would do in a like imperative language. Imperative languages often do this auto layout stuff that they kind of like go grid by grid and try to find a path and do stuff like this. But we need to kind of like break it down in a more functional way. So what we first do is we kind of like replace every function block with a node in a graph and ignore all the details. And then just have these connections like a graph, like which function block is connected to which other function block. And these annoying numbers that have been there from the beginning, which shouldn't have been, kind of like forgot to kind of like make them disappear and reappear. That's kind of like weights on the edges, and the weight means how many of the real connections are actually between those things, because we kind of like care about that. So we built a simple graph, and now we kind of like need to figure out how to lay out. So the first step is how to lay out where every function block goes. Like this is a grid layout, and it's kind of arbitrary. We did not like specify anything in advance. So no. So that's kind of like a kind of simplified graph. Like taking away from the thing. So that's like the blue thing is our function blocks, and the weighted edges our graphs. And the first thing we have, we kind of like want a layered approach. So we want layers which are connected between each other. So that's called layered graph layout. But that doesn't work very well when you have loops in your graph. And we have loops here. Like, can spot several loops. How many loops do you see? There are several. And the first thing is you take away the loops, basically. And there's a trick. If you do this right, and you do the minimum feedback arc set, that's an algorithm that you run that basically takes away the lowest weight, because that kind of like disturbs the less, and turns it around. So we flip the arrows around until we have a directed acyclic graph. No loop anymore. And a directed acyclic graph, now we basically need to figure out how to lay out this from left to right in like grid rows, but we already have a certain order. But we need to do more. The thing is, we need to do transitive reduction. So what's transitive reduction? Transitive closure, you might have heard of. That's when you have like some relation, and you add all the combinations of all the relations to your set. So let's say if you would have like arrow 6 on the left and arrow 2, then you would also add arrow 4. Because you can go 6 and then 2, and then you add the arrow 4. And transitive reduction is the reverse of this. So you take away everything that you can reach over a longer path. Which is kind of like weird, but yeah. Normally you don't want this. So you take away this 4, you don't need this. And there's more you can take away. Because you don't need this 2, you can go over 4, 5. Are we done already? No? I see shaking heads. Yeah, because 5 is totally superfluous now. And now suddenly we have a very simple structure. We actually know the order already. So from left to right, because what we don't care about is like when a layer has connected to another layer, that you want to have them behind each other. But if there's another connection to a further layer, you can't avoid jumping one layer. That's unavoidable. So you take them away, all these superfluous jumping things, and you are left with a much simpler directed acyclic graph then. So and then I couldn't figure out to make a drawing for that, and it's actually too complicated. So I really very hand-wavy. Like, the algorithm is called Graham-Kaufman, and it's interestingly can be used for graph layout and also for multi-core scheduling. Because this like column graph layouts assume like the rows are cores and the columns are steps in a process, and that would be a statical schedule on this. And it's the same algorithm. It's kind of funny. So what you actually want to do is you want to topological sort your directed acyclic graph. So you get a directed acyclic graph, you can do a topological sort where no error goes backwards, basically. In our graph, it was too simple because it's already done. You have one order. But normally there's more than one order. So there's more than ways to kind of like skin this cat of the topological sort, and you want to do the one that looks best. And that's what the Graham-Kaufman algorithm does. I think we are a little bit short on time, so I skip over this. Basically, you start with all the nodes that don't have any input, because they need to go left. And then you figure out all the nodes whose whole input set, like all incoming arrows, come from other nodes that already have a number, which you already labeled, because that needs to be the next layer. And in the order you bring them, you do a lexicographical sort of this, like you put all the weights of all the incoming arrows and sort those, and then do a lexicographical sort of all those arrays, because then you kind of like stay close. The closer things stay further up, and then you basically fill it up into columns. And you basically have the only parameter that goes in is the number of nodes you can have in a column. Then we need a few other things, because we have this placement now. That's actually the placement you get from this algorithm. So it's like less columns on the left, because we didn't want to squeeze it up too much, because it would add a lot of confusing to and fro things. It's already quite confusing, but that's kind of like unavoidable confusability here. But you see that there are a few errors, because that's the stuff that we took away before, jump over one column. So they go, because we reduced the problem, and we didn't jump over columns before, but now we need to add this jumping columns lines. So that would be those lines, for example, or those lines going between the function blocks. And we just add like a kind of like pseudo node into this column, which only consists of this horizontal line, which then breaks down the problem that you only need to kind of, you only, with quotes, have to deal basically with the stuff that goes on between two columns. So you're breaking down further the problem into simpler problems. And what we then do is we swap the order of the nodes in one column until you get the minimum amount of crossings. There's some complication I left over, because you always have backwards going arcs, and you have these loops that go there, and so the crossing number is actually not easy to calculate. And also you probably want to like add into the heuristic like the length of the lines, because sometimes you avoid crossings, but then it goes around the whole thing, so you don't want this too. And that's like additional things that we do. And then we end up in this thing. So then we only need to draw these little corners between the thing, which is another quite complicated algorithm, which we don't have time to explain anymore, which is fortunate, because I don't have slides for them. Because I kind of like, yeah, I don't know how to explain this in 45 minutes. And we're done.